Hello class, I wanted to finish the explanation that I rushed through at the end of the last lecture, so this is lecture 15C, and that is calculating gradients using the parent domain coordinates. So let's assume you have some quadrilateral in the xy plane with nodes 1, 2, 3, 4, and each node has coordinates x1, y1, x2, y2, x3, y3, x4, y4. I guess I should also add the e because this is for this particular element, and I want to map that to some common space, some common quadrilateral, which I'm gonna call the parent domain in the coordinates xi and eta, and that one has nodes 1, 2, 3, 4, minus 1, minus 1, 1, minus 1, 1, 1, minus 1, 1. So I want to map these two, and the map is defined, is called the isoparametric map, which is the x as a function of xi and eta is going to be the sum of the shape functions, which I can easily define in the parent domain. We did that last class, times the node of x coordinates, and y is the sum of the shape functions defined in terms of the parent domain coordinates times the nodal y values. So this is the map between x, y, and xi eta. And all it needs is these shape functions in terms of xi eta. So given the map, we also talked about how to get the Jacobian of the map. The Jacobian of the map is basically the derivative of the map. So the derivative of the xy coordinates with respect to the parent domain xi coordinates. So this is a 2 by 2 matrix. So this would be the partial of x with respect to xi. This would be the partial of x with respect to eta, the partial of y with respect to xi, and the partial of y with respect to eta. And since we have the map up here, these partial derivatives just depend on taking the partial derivatives of the shape functions. So for example, the partial of x with respect to xi I can get from here, which is just the sum of the partial derivative of the shape functions with respect to xi times the x coordinates, and this one will be the sum of the partial derivatives with respect to eta times the x coordinates, and then for y I just need to copy paste. So given the shape functions and the xy coordinates, I can get the map and the Jacobian of the map. That's all I need. So that's on one hand what we have, and this is called the isoparametric map. Now, suppose that I have a function that I want to interpolate over the domain. And usually we have been using theta. And now what I'll do is I'll use the shape functions in the parent domain, which are the ones that were introduced in the lecture. So a function interpolated over the parent domain will be sum of the shape functions times the nodal values. So if I have nodal values, then I can interpolate the function. Now the problem is, it's not really a problem, but the function is defined in terms of the parent domain coordinates xi and eta because the shape functions are in terms of the parent domain coordinates xi and eta. But what if I want to get the gradient of a function, which we might need to do? So what if I want to calculate the gradient of theta e, and by that I mean I want the derivative of theta e with respect to x and derivative of theta e with respect to y. Now this is tricky because I have theta e defined in terms of the parent domain coordinates, because I have the shape functions in terms of the parent domain coordinates psi and eta, but I need derivatives with respect to x and y. So what to do? Chain rule. So instead of calculating directly the derivative with respect to x, I would take partial of theta e with respect to xi, then partial of xi with respect to x, plus partial of theta e with respect to eta, partial of eta with respect to x, and for the y I would say partial of theta e with respect to xi, d xi dy, plus partial of theta e with respect to eta, d eta dy. So this is what I would need to do. I can rearrange this a little bit. So I'm gonna do this as a matrix vector multiplication. So here you can see that I'm gonna end up with partial theta, partial xi, partial theta, partial eta. And here I'm gonna end up with partial xi, partial x, partial eta, partial x, partial xi, partial y, partial eta, partial y. Just rearranged it a little bit. And so now the question is, how do I calculate these two things? And then first notice that this term right here, this one looks a little bit like the Jacobian. I mean, actually it looks similar to this guy right here. It's just that it's reversed, right? So the Jacobian is the derivative of the x coordinates with respect to the parent domain coordinates, and this is basically derivative of the xi coordinates with respect to the x coordinates. So it's sort of flipped. So what does that mean? That just means that this is actually the inverse of the Jacobian. So if I know how to calculate the Jacobian, because I have it right here, then I just need to invert that matrix, and the inverse of that Jacobian will be this guy right here. So that solves part of the problem. And then the other one is really not a problem. This is easy. Because I have theta in terms of xi and eta anyways. So it's really, I only need to take the derivatives of the shape functions. So just recap. If I want to get the gradient of theta e, meaning I want the derivative of theta e with respect to x and the derivative of theta e with respect to y, what I need to do is I need the inverse of the Jacobian. And the Jacobian matrix I can calculate because I only need basically x and y coordinates and derivatives of shape functions, and I should have that. So the Jacobian I can calculate, then I can invert that matrix, and I have this matrix right here times these partial derivatives, theta e with respect to xi, theta e with respect to eta, and then these derivatives d theta e with respect to xi, d theta e with respect to eta are actually directly available, because this is just the sum of partial n with respect to xi times nodal values, and this is sum of partial n with respect to eta times the nodal values. And that's it. That's how you calculate the gradient of some function. You need the inverse of the Jacobian, and you need the derivatives with respect to xi and eta, which you can have because you have the interpolation in terms of the basis functions in the parent domain defined in xi and eta.